In this video, we're going to look at some advanced concepts in the chapter of acids and bases. The common complaint that I get for this chapter is that sure, I can understand the concepts in this chapter, but for some reasons I can't seem to apply it to many questions. Now the reason is largely because many of the questions actually involve one of the following advanced concepts. So right now we're going to look at some of these questions, and I'm going to use them to explain the concepts in solving these questions. For this question, we are supposed to write an ionic equation for the neutralization reaction between an acid and an alkali. So what is an ionic equation? In reactions involving ions, very often not all ions are directly involved in the reaction. So what an ionic equation shows are the actual ions that are undergoing the reaction. So for this question, there's actually a shortcut, and the shortcut involves asking yourself what is the main ion in an acid that's reacting, or what is the main ion in an acid that makes it an acid, as well as what is the main ion that makes an alkali an alkali. Okay, at this point, I hope you would have gathered that the main ion that's involved when an acid undergoes reaction would be your hydrogen ion, and the main acid involved when an alkali undergoes reaction would be your hydroxide ion. And the reaction of your hydrogen and hydroxide ions, I think very obviously would give you your water. Okay, so the ionic equation of any acid reacting with any alkali would always be as shown. For this question, we are looking at the reaction of a dibasic acid. Earlier in the lessons, we have learned the concept of basicity, which tells us the number of hydrogen ions that we can get from one unit of an acid. For example, sulfuric acid H2SO4 is a dibasic acid because one unit of the acid can produce 2 units of hydrogen ions. Now for this question, we are looking at phosphorus acid. Phosphorus acid has the formula H3PO4. Now something that looks initially strange is that the question tells you that it is a dibasic acid, because very often when we look at the chemical formula of the acid, and more specifically we look at the number of hydrogen atoms in the formula, we can derive the basicity of the acid. For this case, even though there are 3 hydrogen atoms in the formula for phosphorus acid, the question tells you that it is a dibasic acid. So what is going on is that out of these 3 hydrogen atoms, actually only 2 of them can form hydrogen ions. Okay, meaning when we look at phosphorus acid being dissolved in water, it actually ionizes, and only 2 of the hydrogen atoms can form ions. One of them actually remains with the anion. Okay, so therefore phosphorus acid here is a dibasic acid. The main part of this question is asking you for the salts that can form when phosphorus acid reacts with sodium hydroxide. To solve this part, we need to revise something that we have learned about the salt that is formed when an acid undergoes reaction. When an acid undergoes a reaction, the salt that is formed can be obtained by replacing the hydrogen or the hydrogen ion in the acid with a metal or the ammonium ion in the other reactant. So for example, if we are looking at the reaction of hydrochloric acid with sodium hydroxide, the salt form can be obtained by simply replacing the hydrogen ion with the metal ion in your in the other reactant, which is your alkali. So the salt form would be sodium chloride. Okay, another example would be this: if we are looking at nitric acid reacting with ammonia. Okay, so the salt that is formed can be obtained by replacing the hydrogen ion with the metal ion. In this case, we are looking at ammonia, so it's to replace it with ammonium ion. So the salt form is ammonium nitrate. Okay. Now there's one special concept that you need to learn in order to solve this question, and is involving dibasic acids. Now when dibasic acids undergo reaction, remember there are two possible hydrogen ions that can be replaced. So the concept here is this, that the hydrogen ions are actually replaced one at a time, or the hydrogen ions actually undergo reaction one at a time. So when phosphorus acid reacts with sodium hydroxide, what happens is that since phosphorus acid is a dibasic acid, it means that there are two hydrogen ions in there that can be replaced by sodium ions. So the first and as earlier mentioned, the substitution, the replacement of the hydrogen ions occurs one at a time. So the first salt that can be formed, or the first salt that is formed, would be obtained by replacing one of the hydrogen with sodium. So we have two hydrogens remaining, and this is the formula of the salt. And the second salt that we can get would be to replace one more hydrogen with a second sodium ion. So this is the formula of the second salt that can be formed. Okay, would there be a third salt? The answer is no, because the question already stated there is a dibasic acid, so it can only two of the three hydrogens can actually form ions. Only two of the three hydrogens can actually undergo reaction with an alkali. Okay, so the answer here is C. Now there's actually a shortcut for this particular question, and to apply the shortcut you just need to note this, that a monobasic acid will only give one possible salt. A dibasic acid will give two possible salts due to the replacement of the two hydrogens one at a time. A tribasic acid will give you three possible salts. And since the question already tells you there is a dibasic acid, so there are two possible salts that can be formed. And in this question, in the four options, there's only one option that has two salts. So obviously that is the correct answer. In this question, we are looking at the change in pH when we add excess base to an acid. To understand this question better, it will help to have a diagram. So we have sulfuric acid, and we're going to add your aluminum hydroxide into it. At the same time, we're going to measure the pH, possibly using a pH meter. Okay, so to know how would the pH change, we need to imagine, or we need to deduce the pH at different points of the reaction. Now before we add any aluminum hydroxide, what we have in solution is sulfuric acid. Sulfuric acid is a strong acid, so we will expect the initial pH to be around 1. What happens when we continue to add aluminum hydroxide is that the aluminum hydroxide, being a base, would react with the acid. That means that as we add aluminum hydroxide, there will be lesser and lesser acid remaining. So what will happen is that the pH will slowly increase. Now there will come a point where all your acid is reacted away. So at this point, we have no acid present. The solution will be neutral. Okay, the question now is what happens if we continue to add aluminum hydroxide after that. Okay, whether the pH would change following this point depends on whether the base that you have added is soluble in water or not. Okay, in this case we are looking at aluminum hydroxide. So since aluminum hydroxide is insoluble in water, remember only SPCA hydroxides are soluble in water. Upon further addition of your aluminum hydroxide, it cannot dissolve in water, and if a base cannot dissolve in water, you do not get any hydroxide ions. Your pH will not increase beyond 7. Okay, so for this question, the answer is actually A. Okay, reason being your aluminum hydroxide cannot dissolve in water, therefore no further hydroxide ions will be formed. Now, should I change the question where I change the base to sodium hydroxide? Now, sodium hydroxide is soluble in water, so after all the acid has been reacted, if I continue to add sodium hydroxide, your sodium hydroxide will dissolve in water to produce hydroxide ions, and the pH will slowly increase until it reaches around 14. Now this question is very similar to the one before, just that now we have a visual representation of the change in pH in the form of a graph, which we call the pH curve. In this question, we are looking at the addition of copper 2 hydroxide to hydrochloric acid. So again, to explain the shape of the graph, we need to look at the certain points in the addition. The first point we will look at is here, where we have yet to add any hydroxide. So before adding of any copper 2 hydroxide, what we have in solution is hydrochloric acid. Hydrochloric acid is a strong acid. Okay, therefore the pH is very low, it's around 1. Okay, the second point that we look at is where the pH slowly increases as the mass of hydroxide increases. So how do we account for that? Is because when we add copper 2 hydroxide, your acid is reacted away. Okay, when your acid is reacted away, the concentration of hydrogen ions would decrease. Therefore, the pH will slowly increase. The third point that we'll look at is where the pH reaches 7. So when pH reaches 7, it means that all the acid has been reacted. Okay, and since all your acid has been reacted, the pH will be a neutral pH where it's 7. Okay, the last region or point that we need to explain is why the pH remains constant at 7. Okay, once again, we are looking at copper 2 hydroxide. Copper 2 hydroxide is insoluble in water, and as a result, it doesn't, when we further add copper 2 hydroxide into the solution, it doesn't dissolve. When it doesn't dissolve, it doesn't produce hydroxide ions, so the pH will not increase beyond 7. This is the second part to the question, where if we were to change copper 2 hydroxide to sodium hydroxide. Now earlier we have mentioned this, that when the base is being changed to sodium hydroxide, which is soluble in water, the pH actually goes all the way up to 14. Now how would the pH curve look like? It actually looks something like this. Okay, we call this a sigmoidal shape. Now why exactly does it look like this? It has nothing to do with chemistry, it's more about mathematics, because pH is actually a logarithm function. Okay, in fact, pH is minus log of the concentration of H plus. Now because of the logarithm function, there will come a point in the pH curve where a small increase in or rather a small decrease in the concentration of hydrogen ions will lead to a drastic increase in the pH. Right? So once again, the shape of a pH curve when sodium hydroxide were to be used, or any soluble alkali were to be used, soluble strong alkali were to be used, will look like the sigmoidal shape that I've drawn. Reason why it looks like that is more mathematics rather than chemistry. For this question, we are looking at the reaction of acid with carbonate. Okay, we have learned in lessons that acid react with carbonate to give salt, carbon dioxide, and water. So the question now is asking you, for a particular pair of substance, we actually do not get a lot of carbon dioxide coming out. Now what is the reason for that? Let me point out the answer to you first, and then I'll explain why for this particular pair of reactants you don't get a lot of carbon dioxide. The answer to this question is C. Now what happens when we react barium carbonate with sulfuric acid? The issue here is that the salt that is formed is barium sulfate. Okay, so the issue with barium sulfate is that it's actually an insoluble salt. Okay, so barium carbonate is a solid. Now what happens when barium carbonate reacts with sulfuric acid is that the salt, since the salt form is a solid, it will actually form on the surface of your barium carbonate. Okay, meaning there will be an insoluble barium sulfate layer on the surface of barium carbonate. And once you get this layer forming on your barium carbonate, what happens is that it will prevent any further reaction with sulfuric acid. Okay, so it blocks any further reaction between barium carbonate and sulfuric acid, and because of that the reaction will actually stop before your barium carbonate is fully reacted, and because of that you will not get a lot of carbon dioxide. Okay, now this is not limited to barium carbonate reacting with sulfuric acid. As long as any solids reacting with an acid produces an insoluble salt, the insoluble salt will actually form an insoluble layer on the surface of your solid reactant and prevent it from further reaction. So this is the second example that we're going to look at, where we are now looking at the reaction of a metal with an acid. Now earlier in the lessons we learned that not all metals can react with acids, only the reactive ones do. In this case, lead is actually reactive enough to react with acid. However, if we were to react lead with sulfuric or hydrochloric acid, you'll find that the reaction actually stops even before it's complete. Okay, so the reason for this is the same. When lead reacts with hydrochloric acid, for example, the salt that is formed, is actually your lead 2 chloride, and we have learned in the solubility rules that lead 2 chloride is insoluble. So this is the case where your product is insoluble, and what happens is that you will form on a layer over your lead. Okay, and once this layer forms, it will prevent any further reaction between lead and your hydrochloric acid. Therefore, the reaction stops even before lead is fully reacted. In this question, we are looking at the reaction of an acid with a metal again. So the metal that we are looking at is aluminium, and it's a very famous metal in this chapter. Okay, so when we react aluminium or any metal with an acid, by right we should see bubbles, bubbles being your hydrogen gas. But when you throw aluminium into an acid, you'll find that at the start there are no bubbles. So it will take probably about 2 to 3 minutes before you start to see any bubbles appearing. So what is the reason for that is this. This is unique to aluminium. Aluminium has a high tendency to react with oxygen in the air. So if I pass you a piece of aluminium, very likely the surface would have reacted with oxygen in the air to form aluminium oxide. Okay, so when you throw a piece of aluminium into an acid, okay, it's actually covered with a layer of oxide. So the layer of oxide will actually react with your acid first, for example nitric acid. Okay, and when an oxide, being a base, when an oxide reacts with an acid, we actually get salt and water. Alright, so there's no gas being produced. So that's as a result we do not see any reaction going on. So it's only when your oxide layer has been fully reacted, only then can your aluminium react with your nitric acid to produce hydrogen gas. So only you have to wait about a few minutes for your oxide layer to be completely reacted with the acid before your metal reacts with the acid to give you hydrogen gas. In the next two questions, we're going to look at the writing of chemical equations for the reactions of acids, and these are the slightly trickier equations to write. The first of which involves the reaction of aqueous ammonia. Now, when students write equations for the reactions involving aqueous ammonia, they often get stuck. Okay, why? Is because they would recall from lessons that alkalis react with acids to give salt and water. So the salt here is ammonium sulfate plus water, and then they will get stuck trying to balance this equation. Okay, the reason for that is the inclusion of the water in the equation. At this point, it is good to revisit the concept of why aqueous ammonia is an alkali, even though we do not see any hydroxide in the formula. In order to see how aqueous ammonia acts as an alkali, we need to see the reaction between ammonia and water. So when ammonia is dissolved in water, it actually undergoes a reaction to form ammonium and hydroxide ions. So that is why aqueous ammonia is considered an alkali, because it reacts with water to form your hydroxide ions. Okay, so strictly speaking, when you're writing the formula, when you're writing the equation involving aqueous ammonia, we need to add in the water in order for the hydroxide ions to be shown. Okay, and in writing of chemical equations, it's very similar to mathematics. If we have the same substance or we have the same unknown appearing on both sides of the equation, we actually cancel it away to simplify the equation, right? So as a result, when we are writing the chemical equations for the reactions involving aqueous ammonia, right, even though water is produced in the product, we do not feature it in the equation. For this question, we're going to write an equation for the reaction between zinc and ethanoic acid. So zinc plus ethanoic acid would give us a salt plus hydrogen gas. So the difficulty with this question lies in writing the formula for your salt. Okay, for that, it's important to remember this, that salt is an ionic compound, is made up of a cation and an anion. The anion actually comes from your acid. So the acid over here is your ethanoic acid, and when ethanoic acid behaves like an acid, it actually forms your ethanoate ion. Okay, so this is CH3COO minus. This is known as your ethanoate ion. Okay, and the cation actually comes from the other reactant. The other reactant here is zinc, so your cation is zinc ion. Bear in mind that zinc, the charge on your zinc ion is something that you have to memorize. Zinc is always 2+. Right, to get the formula of the salt, now we need to use our rules for writing chemical equation for chemical formulas for ionic compounds, which is to make sure that the charges cancel out. Right, in this case, since we are looking at 2+ and minus, we know that by combining them together, the charges do not cancel out, and to ensure that they cancel out, we need to pair one zinc with 2 ethanoate ions. Okay, so this is actually the chemical formula for the ion that is formed, for the salt that is formed. Now, in some textbooks, especially at higher levels, you'll find that the order of the ions is actually swapped. Okay, This goes against the rules that we have learned in the topic of chemical formula, but there are good reasons for doing that. I shall not elaborate over here, but in the context of O levels, both ways of writing would be correct. Okay, and if you want to be consistent with what we have learned in the syllabus, is that we always write the cation first followed by the anion.